Connected by purpose, driven by passion. This is Children's Healthcare Canada's Spark Live webinar series.
Children's Healthcare Canada would like to thank our Keystone funding partners for their ongoing contributions that support all of our programs and activities, including this Spark Live weekly webinar series. Spark Live is where we gather each week to curate, convene, and showcase excellence and innovation from across the child and youth healthcare community. Our goal is to spark conversation, ideas, and action. There are two options to join in on the live conversation. Questions and comments for our panel or presenters can be typed into the question box, or comments that you want to share with the audience can be typed into the chat box and be visible to all of the attendees. For those of you on Twitter, tag @ChildHealthCan on any webinar-related tweets or use the hashtag SparkLive. And to keep up to date on all of Children's Healthcare Canada's webinars and other activities, be sure to sign up for our weekly Spark Bulletin by visiting our website at childhealthcan.ca.
Hello, everyone, and welcome to a new edition of Children's Healthcare Canada's Spark Live webinar series. I'm Paula Robeson, your host for the next hour. Children's Healthcare Canada acknowledges that our offices, located in Ottawa, are on the unceded, unsurrendered territory of the Algonquin Anishinaabeg people. We recognize and deeply appreciate their historic connection to this place. We also recognize the contributions that Métis, Inuit, and other Indigenous peoples have made, both in shaping and strengthening this community, our province, and the country. Today, we're delighted to bring you Imaging the Invisible, Lingering Brain Dysfunction After Pediatric Concussion. Just a reminder that we record all our webinars, and as mentioned in the introductory video, please type your questions into the question box as you think of them. I'll prompt you via the chat as well, and I will pose the questions to our speaker at question breaks throughout the session. Now I'd like to introduce our speaker today. Dr. Ben Dunkley is a scientist and diagnostic imaging and the neurosciences and mental health program at SickKids and assistant professor in medical imaging at the University of Toronto. Ben studied for his PhD at Cardiff University in the UK, and he completed his postdoctoral training at SickKids. And his current research program focuses on the disruption to neural function and circuits in health and disease in children and adults. It's my pleasure to pass the mic to Ben.
Hello, everyone. It's fantastic to be here today talking to you about my research. Wonderful invitation from Children's Healthcare Canada. And as mentioned by Paula, I'm going to be talking about imaging the invisible, some of the really fantastic, I think, developments in scientific imaging and clinical neurosciences where we can now start to understand and unravel some of the lingering brain dysfunction after what we call the silent epidemic of concussion. So for today's talk, there's three main components, really. I'd like to give a bit of a background to some of the neuroscientific themes and approaches that we use in our research. Sometimes the language and terminology can be quite complicated, so I always like to make sure that, this is delivered in an accessible manner for everyone to easily understand. In the second part of the talk, I'm going to talk about our work to date looking at concussion and how that disrupts brain activity, specifically neurodynamics and those brain circuits that control our behaviour and cognition. And then finally, I want to highlight some of the really exciting future research directions in my lab and others that we work with, including some really quite exciting emerging technologies, the use of AI or artificial intelligence, and new therapeutic approaches as well that we can treat brain disorders. As Paula mentioned, I've interspersed throughout the talk a number of question sessions, so please feel free to obviously, deliver those within the chat, and then, at points within the talk, I can sort of pivot back and try and answer some of those questions that you might have. Of course, if the video feed is choppy or the audio, please let us know, and I'll do my best to try and rectify that. So let's get going. So I always like to talk a little bit about the human brain. It's really the most incredible organ and probably the most complicated thing in the known universe. It really only constitutes about 2% of our total body weight, but it consumes about 20% of our oxygen intake as well as our energy, and it generates about 10 to 20 watts of energy output, so more than enough to power a light bulb. And it's really 90% composed of water and fat. But within that, there are about 100 billion neurons. So these are like the electrical processing unit, the central processing unit, to think of analogy in computing, the information processing unit of the brain. And between these 100 billion neurons, there are at least 100 trillion connections, forming, these circuits and supporting their function are 160,000 kilometers of nerve fibers and blood vessels in the brain, right? So it's this incredibly complicated organ. It looks like this gelatinous pink gray blob essentially, but the complexity is bewildering, and it really is the center of all of our thoughts, feelings, memories, our actions and behaviors that we will ever have. So, as I said, the neuron is really this basic unit of processing within the brain, and we can see a schematic here, and it looks quite simple, really. That there's the one end which comprises of dendrites and the nucleus, and then there's an axon that's covered with a fatty myelin sheath to aid conduction, and then there's an axon terminal which connects onto other neurons within the brain. But essentially, it works through the transmission of electrical impulses that travel from one end to the other, and then through a series of processes at the synapse, that signal might be transmitted onto the next series of neurons. So these control all of our behaviors and thoughts and feelings, as I just said. Now, as a cognitive and clinical neuroscientist myself, we really want to be able to understand the brain, its basic functioning, but also how it goes wrong, and how that can tell us about disease states, some mental health challenges, a neurological illness. So we have these behaviors as well as our internal thoughts. Obviously behaviors are kind of observable and we can objectively measure those. In cognition, it's a little bit more difficult. You have to ask people about that or test them using experiments. And we understand that the brain is comprised of many, many different cells, many different cell types, which comprise molecules, this reductionist approach, moving on down to the different levels of complexity. But we also know that different areas of the brain have specialist functions. So one area of the brain deals with your language function, one area of the brain deals with your vision, one area of the brain deals with your motor output and memory, and so on and so forth. And this was driven by 100 or so years, even more, of neuropsychology. Where we see damage to one bit of the brain, we can infer what that area of the brain does, essentially. But over the last 20 years or so, we've really been informed by connectomics, or brain circuits, and what we realize is that each of these areas in isolation are obviously incredibly important, but it's how they talk with one another and organize information which really gives rise to us as people and the human condition. So we have different levels of complexity and spatial scales when we talk about the brain, and it is difficult in neuroscience, but we're trying to integrate all of them to fully understand how the brain works, really. So we can measure the brain network architecture, we sometimes call it. And in human neuroscience, and animal neuroscience really, we divide them quite broadly into structural and functional aspects of networks in the brain. And here we can see a structural network in the brain. These are these beautiful white matter pathways, those axons, those myelinated axons, which connect areas of the brain to do the computation, to do the information processing. And you could think of these as kind of the wires that might be in a computer or circuits on a circuit board, say. And we have special imaging techniques which allow us to pull this information out of the brain, and scan people non-invasively. Complementary to that, we can also look at the function of the brain. So you've probably all heard of Fmri, which is an incredibly powerful technique which tells us about the function of the brain, and we can look at how different areas of the brain turn on and off. And from that, we can figure out networks and how different areas of the brain are talking to one another, really, to support our behaviors and thoughts. Classically, or quite ubiquitously, we use MRI for a lot of this. It tells us incredibly detailed information about brain structure and brain function, DTI and Fmri. But there are also complementary techniques which tell us about the activity in the brain, to which MRI is essentially blind. And one of those is Magnetoencephalography, or MEG. You might have all heard of EEG as well. This is another way that we can look at brain activity. And it tells us about brain function. It doesn't tell us anything about the size or the shape or the structure of the brain, but it gives us really an insight into the workings of the brain, which we can sometimes miss. So MRI is extremely common these days. Many of you might have had one for various purposes. It's used in diagnostics and monitoring, as well as brain research. And it relies on magnetic properties of hydrogen atoms in the brain and the water and fat to look at the tissues and their boundaries and delineate them. And we can apply different pulse sequences, different magnetic pulses essentially, to look at different types of information in the brain. And here you can see kind of a characteristic MRI image that, you know, a radiologist might look at to diagnose a brain disorder. Unfortunately, it doesn't really tell us anything about those electrical properties of the neurons that are firing. You know, it gives us this incredibly detailed view of the brain, you know, sometimes down to less than 1 millimeter of resolution, really. But it doesn't tell us about neural firing. As I said, you know, one of the ways that we can look at that, and one of the ways we look at it at SickKids, is using MEG. So I'm incredibly fortunate, you know, to work at Hospital for Sick Children, and we have access to some really unparalleled equipment to really understand the brain. And here's our MEG system that we have installed here, and you can see there's a bed, and people would come and lie down on it on their backs, and they place their head in the scanner just here, and you know, we can kind of deliver stimuli to them, you know, so they can maybe perhaps engage in a memory task, or we can show them faces, or you know, get them to do a language task. We have button boxes and other equipment, so we can kind of monitor people's behaviour while they're thinking inside the MEG, and we can record all of that ongoing electrical activity. So it's really quite cool, the kind of aspects of brain functioning that we can probe using these technologies. I don't want to get bogged down in, you know, the science and the physics behind everything, but it's incredibly fascinating to me. You know, so MEG records these tiny magnetic fields in the brain. And the magnetic fields are so small, you know, they're many, many orders of magnitude smaller than either the Earth's relatively weak magnetic field, and those magnetic fields generated by your heart, or even just everyday objects like hair dryers and shavers and what have you. And we have to keep these sensors cooled at minus 269 degrees Celsius. That's almost absolute zero, you know, colder than deep space. So it's quite an engineering challenge, really, to understand, you know, brain activity. But these incredibly sensitive tools allow us to kind of look in the brain from where the activity is coming from when someone is thinking and behaving. And, you know, a nice analogy is to say, you know, searching for a needle in a haystack, or I think a better one is really hearing a pin drop at a disco. You know, that's really quite the incredible physics and engineering behind some of these technologies, which is sometimes easy to overlook. So the technology is, you know, fantastic for doing these kind of experiments, and we can look at brain activity down to 1/1000th of a second, so, you know, a millisecond, you know, which is hardly anything at all. And we can localize that in the brain down to a resolution of less than about 5 millimeters. And unlike Fmri, which measures blood hemodynamics in the brain, you know, changes in blood flow, it's a direct measure of those electrical circuits. And, you know, for a lot of anxious individuals, you know, a lot of individuals who might be who might not well tolerate MRI, if you've had one, you realise how noisy it can be. It's actually far less intimidating, and it's less messy and quicker to set up than EEG, but it is expensive. So there is that. So I'm just going to go back 1 second, and we can look at this activity at the speed at which someone is thinking. You know, so here's a nice example, I think, that really is testament to that. Here we can see someone's MRI image, you know, and we can see the size and the shape of the brain and all those convolutions and you know, gyri and sulci. And you know, it gives us this really nice view of the brain and the size and the shape in the different areas, but it's a bit of an impoverished view because it doesn't tell us about the electrical activity, which we see here overlaid on the brain, you know. And this is all happening within thousandths of a second, you know, or perhaps a little bit longer, say. But, you know, MRIs don't tell us about this. And with MEG and EEG, we can look at this. And this is occurring, you know, many, many times a second as someone is thinking, you know, as they're maybe thinking about what they're going to have for dinner tonight, or recalling what they did the day before, or, you know, thinking about playing tennis later on. You get activity in all these different areas. So it's incredibly dynamic. It has this repertoire that we can sometimes miss when we think about the brain, you know, just as this purely static organ. So one of the ways that we now view the brain is by looking at brain waves. I'm sure you've all heard of this, but it's a way for the brain to process information and organize our thoughts and behaviors. So if we were to record from an area of the brain, what you find is that you get these brain waves. You know, and this is reflecting many, many neurons firing simultaneously in an area of the brain, right? So it might be the area that deals with your visual perception, and you find that they rhythmically fire. So these are called brain waves. And they operate from very, 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 very fast down to very, very, very slow. And different speeds are characterized and related to different aspects of your behavior. So when you're engaged in like active thought, maybe doing a math problem or remembering something, your brain activity is very, very fast. Conversely, when you're asleep or anesthetized, say, that activity slows down. And there are other ones as well related to learning and memory, which I won't go into too deeply, but they vary by their speed and their amplitude. And we can, relate these different characteristics of your brain activity to various behaviors. So, for example, if we had someone lying in the scanner, which we do, and we just said, just stay awake but daydream, what you find is you get these very slow, quite large, slow waves, we call them, and the very, very fast waves associated with thinking are suppressed, and we don't really see those. But if we now get you to think about a task, we find that the very fast activity starts bursting and starts going, and the very, very slow activity diminishes and goes away. And these characteristic profiles tell us about the underlying function of your brain, and conversely about dysfunction in the brain, in perhaps mental health challenges or mental illness or what have you. And these phenomena are actually used by a lot of commercial brain sensing and brain stimulation headbands that you might have heard of, including Muse and Think and MellowMind, which use neurofeedback and mindfulness approaches to be able to for you to tune your own brain waves and tune in on them and, really concentrate on your internal state. So that the actual way that we envisage the brain is the same here with these commercial pieces of equipment as it is with MEG. Obviously there are differences in how well they pick up the signal, but they're based on the same principles. And in neuroscience, it's developing rapidly, but we now think of the brain really as a big network, with hubs in the brain, and some are more important than others, and some are connected to many, and some are connected to fewer. And when we sort of analogously compare it to, say, the North American airport, and airline network, you see here that some airports have a lot of traffic going through them and some less so. And if one of these was to be, say, knocked offline by injury or disease, that has to be rerouted through the brain and moved to different areas. But what the key point here is that damage to one area can affect the whole network. It's not necessarily the case that damage to, say, if an airport was to go offline because of some technical problem, that then all the information has to be rerouted. So, we know that now minor disruptions to one area of the brain can actually have a global effect on many different areas. So this is important to keep in mind as I talk about some of our data later on. And we can exploit this to look at networks in the brain using MEG and these brain waves. So we look at different areas and we say, okay, this area is involved in this aspect of functioning and this other area involved in a different aspect of functioning. And we can quantify how much they're talking with one another and how much communication is going on between areas, to support these networks and your behaviors. Conversely, different areas of the brain have to stop talking to one another because, if you're thinking about dinner tonight, you don't want to be remembering, your high school prom, say, or some other aspect. So the brain has to turn off certain areas and inhibit talking between those areas. So, they do this by desynchronizing or decoupling. So the brain, again, is incredibly dynamic, is incredibly complicated. But we now know that, a lot of neuropsychiatric illness, a lot of disordered thinking is actually related to these brain waves and pathological brain waves and connectivity. So this underscores many, many mental health challenges. And here I've got some example data of someone lying in the scanner doing a task. And these are the different areas of the brain lighting up and talking to one another, not in real time, 2.5% of real time. So the actual activity in the brain that supports your thinking is, 40 times faster than what I was just showing there. It's incredibly rapid and it is complex beyond, I think, what we can really appreciate at this point. So I'm aware that we're coming up to a question break. So, points to consider as we reach the end there is that traditional brain imaging is really quite incredible and it's really pushed forward medicine, and it offers this exquisite information about brain shape, size, and many disease states. But it doesn't really tell us about the dynamics and complexity of neural firing and neural activity that underlie all of our thoughts, feelings, and memories. And we now know that, single areas of the brain don't work in isolation. They need to work in concert. And Conversely, when one of those areas becomes disrupted, either through injury or disease, it can impact the whole brain. We now know that, knocking out one hub can actually have a consequential effect on many different other areas. And I really believe that, studying the electrical activity of the brain and brain waves allows us to determine how the brain processes information and how it goes wrong in disease states. And I think understanding that, we can really begin to develop targeted therapeutic approaches, which will be the third part of my talk coming up. So with that, I'd like to open up for questions. If there are any, that would be great to hear from you.
Thank you, Ben. Right now, there are no questions, but I'm just going to give a moment for folks to type in if they have any. Seeing none coming in, perhaps we can continue and take the rest of the questions at the next break.
Absolutely. So hopefully everyone, has understood and appreciated the kind of complexity that we have to deal with in neurosciences and understanding the brain. And of course, if questions do come to mind, feel free to use them in the next session. But we've now begun to apply these approaches to understand, I guess, the invisible injuries that, we often don't think about, particularly in psychiatric illness. I've done a lot of work in the area of PTSD, for example, and that's a big area of research in my lab, where, these are quite debilitating disorders, but they don't have readily identifiable brain abnormalities that we can see with MRI. And we've also now been transferring some of the work that we've previously done in PTSD to concussion, which we think of as a neurological injury, right? It's a brain injury, a physical brain injury. But how can we use these approaches and our prior understanding of psychiatric disease to apply this to concussion and how it disrupts the brain and how it affects communication and cognition? So I think rightly concussion has been termed now the silent epidemic. There's been a huge increase over the last sort of 5, 6, 7, 8 years in terms of emergency department admissions. In terms of sports-related injuries, they're massive. And obviously, of course, with sports like skiing, snowboarding, ice hockey, cycling, they're actually quite common. And we usually think of concussion really as a young male injury, particularly risk-taking behaviours, impulsive behaviours. But the data actually suggests that, it's far more common in very young children, as well as the, elderly who might be prone to slips and falls. And it's actually probably lowest in people that groups traditionally think of as being more concussion prone, but it's probably because it seems to be more readily understood that playing sports and what have you carries this danger with it. And then these are high functioning adults usually, and then a concussion can obviously change that quite quickly. But with the very, very young and very, very old, maybe other things might get in the way to really understanding concussion. So we don't really quite think of it as a young male injury anymore. And certainly for the same sports played and accounting for time played, girl and women are affected more by concussion, and they have greater rates of lingering problems after a concussion. And, we used to think that children are developmentally quite plastic. They have a great degree of brain plasticity, and that it probably doesn't affect them quite as bad as we think. But I think that view is changing. We understand that concussion in childhood can actually alter the way that your brain develops, given the rapid neurodevelopmental change of childhood and adolescence. And this actually, confers a greater risk for lingering symptoms that can really impair their intellectual and social development quite profoundly. So, what is a concussion? And I'm going to interchangeably refer to it as mild traumatic brain injury throughout this talk, but really the definition is a little bit more subtle than that, concussion being a type of mTBI. But we consider it a closed head injury that results in a transient impairment to mental functioning. So we don't define it by structural damage. We define it by an inability to, perhaps momentarily have impaired mental functioning, not remember where you are, not remember what's going on, not quite, be within the place and time that you are. And it comes about usually from, a head impact, but you don't actually have to take a knock directly to the head. You can get a whiplash type concussion from, being hit in the body, or if you're in a car and you're hitting the side of the car and the car spins round. Those acceleration, deceleration forces cause your brain to, move around inside your skull. Your brain is sort of floating really within a bath of cerebrospinal fluid of liquid, and that provides some degree of protection. But your brain still manages to move around inside your skull quite a lot. So the exact mechanism and the damage is multifaceted. But if you remember some of the slides I showed earlier on, you have those wires that connect different areas of the brain, and they're quite diffuse and distributed. And they're actually, very, very thin, and they're particularly susceptible to damage from the head being knocked around. So that causes tearing, an injury to those axons. And then there's sometimes, there often is, what we call a neurometabolic cascade. And this involves changes to, your excitation in the brain and changes in the neural depolarization, altered metabolism. So these all sound quite complicated, but really the consequence is that those neurons being able to fire is impaired. So naturally, the way that we think and behave is also impaired from a concussion. And the symptoms are complex, they're heterogeneous. They're not always the same in individuals, but include headache, dizziness, changes in mood and behavior, amongst others. Now, most of the people who do have a concussion, actually represent about 75%, if not more, than the entire cases of traumatic brain injury. So, it's by far and away the most common type of brain injury. And only a small minority present with real kind of debilitating deficits or disability. But that's not to say that it's still can be quite life-altering. So after a head trauma, you have this both diffuse sort of network-wide effect as well as focal injury on the brain that involves brain damage. And this can be expressed as different types of symptoms, headache, nausea, as we've said. And usually, most people actually spontaneously get better within about 3 months. The majority of cases will, with appropriate rest and care, get better. But a significant minority, and it depends on the population you look at, report lingering changes, 20 to 30% in some cases, cognitive problems, emotional problems, behavioral problems. And the fact of the matter is that if you haven't really recovered after a year or two, you're probably not going to fully recover. And, I think the insidious impact of concussion was brought to light by the case of Rowan Stringer. So some of you might have heard of Rowan. She died in 2013, excuse me, after a second concussion playing rugby. And, this was quite devastating, really, but she died from second impact syndrome. And there was a coroner's inquest and inquiry, which really cast quite a harsh light on sports organisations and their lack of awareness about concussion and concussion protocols. And this, established mandatory requirements in Ontario about reviewing concussion legislation, protocols for removal from sport, and codes of conduct. And now there's been, I think, a transformative change in Canada in sport and beyond. And I think this is, again, highlighted nicely by this commercial that we often see on TV. And it starts out and you think it might be about Nike or Adidas, and it actually becomes, quite striking.
I'm doing whatever it takes, stopping and nothing, I'm up in your face, shaking it off, no matter the cost, I'm feeling the wind, I'm taking it all, I'm kicking the brain with the sweat and the blood, I'm at the top, I'm rising above, I'm on the go, give me the rush, Queen Midas, I got the touch. I'm pushing, 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 I'm pushing.
So I think that video really highlights, how Canada is leading the world in concussion awareness, and certainly how we can address it. So traditionally, brain imaging in mTBI or concussion is quite difficult. As I say, using MRI traditional approaches. If anyone can sort of guess here exactly who's had a concussion, that would be incredible. Obviously, there's a 50-50 chance you can get it, but it's basically impossible to tell. And the image on the right is someone who's had a concussion. So it's invisible on CT and MRI, and it's impossible to tell who has and who hasn't. And there's no gold standard for diagnosing concussion with brain imaging. But is there another way that we can kind of, use those techniques that I described earlier on to look at functional biomarkers to evaluate concussion? So we now know that neural circuit disruption underlies many, many neuropsychiatric diseases. And we really understand that if we can kind of understand brain functioning and brain circuits, we can really begin to maybe start to treat these quite effectively. So using DTI, which gives us these beautiful images of the wiring of the brain, we can look at how there are different connections and connect different areas. But when we apply it to concussion, the accuracy in being able to see disruption is quite low. It's about 20% or less. And this could be due to the heterogeneity of injury or the actual disruption really lying beyond the current resolution of scanners. Technology is always advancing and we're getting close, but it's still quite unreliable at being able to tell who's had a concussion or not. So there's very little clinical use for these techniques just yet. But we can measure the activity of these neurons in the brain using MEG. And as I said earlier on, you get these characteristic profiles of brain activity, right? These brain waves. Now, if someone has an injury and we were to measure those waves, what you find is that they slow down. There's this disruption to how fast they fire, essentially. So you don't need to look at these wiring diagrams, these DTI necessarily. You could actually look at the frequency of brain activity, those neural dynamics, that neural firing. And I think this offers us a really potent biomarker for understanding concussion. So as I said, we've done some work in adults, which really established, some concrete evidence for this and has motivated our work in children. So when we looked at a group with adults with just one single concussion, they've just had a knock on the head, they went up to Sunnybrook, they went into the ED, they had MRI, they had CT, they were found to be clinically negative. We scanned them with MEG. And we scanned them on average about 30 days after they've had a single concussion. And we found that, they reported symptoms of concussion, as we would expect, but they also had problems with attention. They reported symptoms of anxiety as well as depression. So, there seems to be knock-on effects from having a concussion, which occur quite quickly after an injury, on average within about a month. Now, when we looked at MRI and we did a group-level study, we actually found that there was, a small amount of cortical thinning. So in the area of the brain, in the superficial surface called the grey matter, we find that it actually starts to thin and atrophy. And this is, interesting enough, but this is at the group level. It still doesn't hold utility in being able to diagnose and prognosticate in the individual. So as I said, we put them in the MEG as well. And we said, okay, we've got an MRI. They've got no clinical indicators of brain injury, but do they have disrupted neural activity? So here's our control group after we scan them in the MEG, and you can see that there's this characteristic patterning of slow brain activity. So when we looked at those slow brain waves of rhythmic neural firing, we find that there's this characteristic pattern. Now, as soon as we looked at mTBI, it was quite striking, really quite profound, really, straight away, that we saw that there was this slowing of brain activity. So that firing has been disrupted, that electrical activity has really been impaired. And we find that in mTBI or concussion, the activity of the brain slows down quite profoundly. So that's what these red colours here indicate. That means that the brain is slowing down in its activity. So, this was very interesting. And we thought, okay, well, how does that affect how different areas of the brain talk to one another? Now, this diagram might seem a little bit obtuse perhaps, but it's one of the ways that in neuroscience we visualize brain activity. And all we really need to know here is that each pixel indicates how well an area of the brain is talking to another area of the brain. And you can see that, you have this, again, characteristic pattern of healthy brain functioning and communication. And when we look at mTBI, you can see it straight away. You can see that it's disrupted. And then we compared the two and we sort of said, okay, where's this occurring within the brain? And you find that in those that have had concussion, many, many different areas of the brain can no longer talk to other areas of the brain. Their brain waves are out, they're not synchronizing. These areas of the brain aren't communicating. So all of these blue connections here indicate disrupted communication between areas of the brain after one single concussion. And these are people who had a mixed bag of symptoms that they reported. Some were asymptomatic, some had recovered, some haven't. But nevertheless, there was changes in how the areas of the brain were talking to one another. And this is in conjunction with no changes in MRI or CT. So this is an interesting observation, but does it really relate to some of the problems that people report? We, while they were in the MEG, we tested them as well. We gave them we administered a cognitive task. So we administered this thing called the set shifting task, which requires you to pay attention and remember and pick which one of these two coloured shapes matches the one on the bottom. Does it match by colour or by shape? In this case, you can see that this is blue, so it matches with this blue circle here. And we can kind of be a bit tricky about this and manipulate what we showed to the individuals, and then they have to think about it a little bit more, and it gets quite difficult as a task. And I guess an analogous way to think of it would be switching between doing two different tasks. So, you might be answering emails in 1 second, and then someone calls, and you have to pivot to answering their phone call. And we've made an analogous task that taps that in the scanner. And what we find is that when people are given an easy task, they've had a concussion, they can do it just about as well as people who haven't had a concussion. But as soon as we start making the task a little bit more difficult, over many, many trials, they start to fail. They have that cognitive fatigue. They feel like they're in a fog, and they can't switch between doing these things. So they start to find it quite difficult. Now, for most of us in our day-to-day lives, this isn't really noticeable. But if you've had a concussion, this is quite debilitating. It can really affect your performance in your job or otherwise. And when we looked at the brain activity that underscored this, in blue here you see the concussion, in green you see the controls, you see that the neural activity in the brain is greatly diminished. It's really affected by this single concussion. And here you can see the concussion again and how these different areas are talking to one another. And it stands in stark contrast really to controls. So their problems on these tasks are really driven by an inability for different areas of the brain to talk to one another. So, that's quite profound, really, that this underlies a lot of the subtle or otherwise subtle problems that they might have. So what about children? We just finished up a study looking at concussion in children. So the previous case with adults was in the acute phase of injury, not long after injury. With children, we wanted to say, okay, is there lingering impairment long after an injury? So we scanned a group of children, mixed sex, mixed mechanism of concussion. A lot of them had run into the pole at the playground or fallen over or, bumped their head playing hockey. And they were scanned about 15 months after injury. So, they'd come in, they might have had a CT, MRI, and they were discharged and not followed up. But we scanned them with MEG, and we compared them to matched, typically developing peers. And we found that those that came in for scanning, 87.5% presented with at least one persistent symptom, and almost 70% with at least two complaints. And headache and fatigue was the most common, as we might have expected, but irritability, difficulty concentrating, feeling mentally foggy, which relates back to that test that I just showed you that we conducted in adults, where they had a problem, doing a mentally demanding, attentionally demanding task. So this is really in line with some of the adult data. But this is over a year after having their last concussion. So when we looked at their brain profiles, here's an image of the brain, and here's some data that I've taken from the very back of the brain that deals with vision. You can see here, this is the characteristic brain activity we see. And I don't want to get too bogged down in the physics and what have you. But in blue, we have the controls. In green, we have the concussed group. And here we have on the bottom, from 0 to 30, the speed of brain activity. And on the y-axis, the amount of that activity. And you can see that it's strikingly different straight away. There are changes in mTBI that linger on in the brain well over a year after someone's been concussed and discharged and probably gone back to school and playing sports. This, I've now expanded this to all areas of the brain. So here in the center, we see the brain, and here we can see activity in the frontal cortex. These are the areas that deal with executive functioning and memory, as well as at the back of the brain here. And long story short, I won't go into this too much. The activity profiles across many, many different areas of the brain is completely changed by a concussion, and it's what we would call dysregulated. Now, it's still early days, and we don't know exactly what this means, but it certainly would suggest that neural firing totally changes after a concussion. Now, if you remember the adult data that I just showed, similarly, here it is for the children. Here's the quantification of slow activity within the brain in our age-matched, sex-matched control group here, and you can see the characteristic patterning. When we look at mTBI, it's slowed across the entire brain. The neural firing is totally changed, and here's the difference. And that in red indicates a slowing in our concussion group. So over a year later, the brain activity is still not quite right, essentially. Similarly, once again, looking at how areas of the brain communicate with one another. This is how we visualize it just in the field that I work within. Again, the different pixels indicate how well an area is communicating, and you can see straight away after a concussion it changes quite dramatically. And here the blue connections indicate an inability for areas to communicate efficiently with one another. So again, not only is the brain activity slowed down, but areas of the brain can't communicate with one another like we would expect. Okay, so of course the brain is very complex. That's not the end of the story. So we see this characteristic disconnectivity, impaired communication within the brain. But we also found that fast activity within the brain increases. So in those with a concussion, some areas are talking more quickly with one another. Now, I think the main point here is that communication within the brain becomes disorganized. It's related to dysregulated neural firing, and we don't need to look at DTI and MRI to look at those tracks. We can image it using these methodologies. And it's important to remember that more communication between areas isn't necessarily better. You can have intrusive thoughts. Sometimes something might pop into your head that you don't really want to think about. And, as I said earlier on in the introduction, that's defined by how areas sync up and communicate with one another. So here we also see in children who've had a concussion, some areas can't communicate and some areas are communicating too much. And better does not equal more communication. There's an optimal amount of communication that is required in the brain to behave and to develop. So this is really quite fascinating, I think, that there are all these changes over a year later. And I'm sure lots of you have heard now about AI, artificial intelligence and machine learning. And we applied it in our cases here to children with concussion. And we found that, these data and these approaches are remarkably sensitive to picking up this automatically. So, we've developed artificial intelligence routines which can now say, this person has dysregulated, disrupted brain functioning, and it works incredibly well. Here it's almost perfect, and here it is perfect. I think this should be viewed with the caveat that it is a relatively small sample, but it just shows that we can now automate and detect this quite rapidly. So it could prove to be a potent tool for diagnostics, I think, for hidden brain injury and visible brain injury. So why is this research important? Concussions can be devastating. I think in a lot of cases, and I personally know that, I'm sure everyone knows someone who's had a concussion, and many continue to suffer, sometimes in silence. And it's a huge healthcare burden. I think mild can be a misnomer, and we really need to move beyond that. So even subtle deficits impact the quality of life, not just from primary symptoms like headache and fatigue, but have other knock-on aspects, to how we think and how we remember things and how we concentrate. And that, that's really quite a concern for neurodevelopment when people are in school, children in school trying to learn. They're trying to develop relationships with their peers, and this can be really quite a concern, I think. And it also makes diagnosis difficult. These presentations can actually mimic other disorders like anxiety and depression, and really trying to understand whether these persistent symptoms are due to a lingering brain dysfunction, or is it now emergent psychiatric illness, or is it both? We need to do a lot more research to untangle them and really say that categorically this is a brain injury, or this person now has emergent psychiatric illness, maybe depression, anxiety. So we're still a little while away. Research progresses slowly, but a lot of the technological developments are happening quite quickly. Treatment is really difficult for concussion, and oftentimes one size fits all. We're moving towards an era of personalized medicine, and I think AI will help that. And recognizing that people have post-concussive symptoms, I think it's quite getting the recognition they deserve is quite difficult, and the implications are significant if we can elucidate that hidden brain dysfunction and begin to inform our return to play, return to school, return to work protocols. So with that, another question break. If anyone has any questions.
We've got a few questions, Ben, for you. First, from Wade, can you image the biochemical processes happening post-injury in kids?
Yeah, we can to some degree. There are ways that we can measure metabolism in the brain. There's ways that we can measure changes in excitation and inhibition and neurotransmitters like positron emission topography. However, those scans are, for example, PET, require the administration of a radioactive tracer. That needs to be usually developed in-house, and the scans are orders of magnitude more expensive. It's really not practicable, I don't think, to be able to do this. People have studied it, I'm happy to send along lots of literature on this, of course. But yeah, maybe one of the points that I didn't really highlight was that, we need this rapid, quick, well-tolerated diagnostic test, and we can look at those, but they are fundamentally more difficult than some of the ways that I describe here today.
Thank you. Does transient impairment change if in quantity if comorbidities were present pre-injury? So you talked before about some of the exacerbations or emergence of mental health conditions.
Yeah.
Do we know pre-post?
Yeah, so there are lots of pre-existing cognitive risk factors. Yeah, like people with ADHD, for example, impulsivity problems, conduct disorder, certainly, are more likely to suffer a concussion and have, post-concussion problems. Oftentimes you find that those working in high performance, maybe varsity teams or high achieving academics, some of the problems that they might have might be adaptation and otherwise, it's that drastic life change that can sometimes, bring about then depression, anxiety. But certainly there are lots and lots of pre-morbid risk factors related to pre-existing, conditions that someone might have, like attentional problems subtly that might be exacerbated by the concussion, right? And we're really only beginning to understand that. And obviously these sorts of data only come from really quite broad, longitudinal studies over many, many years. But there is some data out there on this, and I'm happy to send around literature on this afterwards.
Oh, wonderful. We could post some of those if you have links or just the actual reference list itself on the CAN after.
Will do.
Can near-infrared spectroscopy be used to image the biochemical cascade in concussion?
So, yeah, we're actually going to be trying some groups at Holland Bloorview, for example, and we're going to be getting our own kit in about May. We can use Fmri to look at brain dynamics, but it tells us, again, like Fmri, about the hemodynamics, the blood changes in the brain. So once again, the actual rate at which we can image the brain change is quite slow, in the order of maybe a second or two. Whereas using MEG and EG, we actually acquire data at 1/1000th of a second. So while they're good at looking at neurovascular changes after concussion, related to biochemical change or neurometabolic change, they don't provide the temporal sensitivity that we do. But saying that, they are a lot cheaper, and you can administer them in environments where people can be doing naturalistic type tasks and moving about. So it really depends on some of the aspects that you want to focus in on, and certainly, the holy grail would be a modality and a technique that combines all of these. Unfortunately, physics makes that very difficult at this point. But it's certainly been used quite extensively, actually, to look at concussion.
Thank you. You talked of second impact syndrome.
Yeah.
Is that the second concussion ever, or within a period of time? Or?
Within a short period of time, yeah. Excuse me. Sorry, I've got a bit of a frog in my throat. So in the cases of second impact syndrome, usually it's within a short space of time and the brain just hasn't had a chance to heal. If someone does have a concussion and then, maybe further out after they've already recovered, there's a cumulative increase in the chance of them having post-concussive symptoms. But second impact syndrome is, when the brain hasn't had proper time to heal and there's a catastrophic swelling. So it usually occurs within the context of a short time window.
Ah, okay. And another question with regard to the other uses of MEG and Fmri, for example, for seizure disorders.
Yes. Yeah, so MEG classically has been used for seizure disorders and epilepsy, for pre-surgical mapping. It's a wonderful tool for finding the aberrant electrical activity that occur in seizures and being able to find where that is in the brain and resect that if all else fails. And that's been its main clinical use. But, we're now realizing that it's quite a potent tool for understanding other invisible injuries, right, like concussion and psychiatric disease. So that's where it's been used, and we use it at SickKids. I have neurosurgical colleagues who use it in cases. They see where the bit of seizing cortex is, and they will resect that, surgically. So that's been historic use, but we're trying to broaden that now to use in other brain disorders.
Wonderful, thank you. I've just posted for the last call for questions. Oh, here's another one. Can you overlap positron, NIRS, Fmri, and MEG, and do? Now, These
Yeah,
are
so I can see the
terms.
question. Yeah.
Okay, you can see it. Yeah.
Yeah. So we are doing that now, Wade. Happy to talk about this offline, because I'm quite wary of time, but we are actually integrating. You can't do them simultaneously, but we've done them all in the same subject, and now we're integrating the networks across individuals. And I'd be reluctant to give away the story right now, but Meg seems to have the superior accuracy in being able to differentiate concussion from non-concussed, and we've compared that with DTI and Fmri and structural imaging. And that paper will, eventually come out. But wait. Okay.
That's it for the questions now. Shall we proceed?
Yep, that'd be great. Okay, so in the final part of the talk, I just want to talk about some of the, the exciting, forward-facing research directions and emerging technologies. We know that an injury can kind of knock out the development of the brain, and we can look at the brain and its development using many different types of neuroimaging techniques. And we know that an injury can perturb the trajectory of normal brain development, and this developmental arc, we call it. And we can relate that to neuropsychology, cognition, and behaviour. Now, these studies take years to do. It requires many different types of data collection and integrating them all, which becomes quite difficult. But I think, we're getting to the stage with advanced analytics where we can start to combine them. And, that relates to Wade's question just there. Can we integrate them? And my lab is working on this now, as well as a number of other labs. And machine learning is really the way to do this, I think. So now pivoting a little bit sideways, brain scanners are amazing, but they are big, they're bulky, they're expensive. They tend to be in bigger institutions. People have to stay still for the entire time, and children moving around can kind of ruin. Otherwise, I say ruin. Can really make it difficult to analyze the data in quite expensive experiments. And they're one size fits all. It's currently one head shape and size really, and difficult scanning children who might be low compliant or not tolerate it very well. Sometimes we have to sedate them. So there's a need for cheaper technology. And how can we inform clinical practice? Well, using our conventional scanner shown here, it's great for adults and children down to the age of about 6, but then it starts getting very difficult. So we've been working with some physicists and engineers, and we've developed some new techniques, and we can now scan down to about less than 6 years old, down to about 2. Infants and toddlers as well. And this is kind of a crazy prototype, right? But it's a kid's bicycle helmet with some holes drilled in and these sensors. It looks kind of cobbled together, but it actually works incredibly well. So there's some very exciting advances. We're getting one of these installed in SickKids, a commercial version of this in April. And now we can start to look at the impact of mTBI in very early life, where children can articulate their symptoms or tell us what's wrong. And they can actually sit there with this on their head and move around a little bit, or sit on their mother's lap or father's or whoever their guardian might be. And it allows us to, really start to understand the, infant and child's brain, really, I think, beyond what we can currently do. And you can see the progression of, this is Professor Matt Brooks here with some of the prototypes on his head. He's a physicist by training, right? So he loves tinkering with all these kind of things. And they're called optically pumped magnetometers. And they're actually 4 times more sensitive than our current equipment. You can see here, this is the sort of close to commercial piece of kit. So, there's exciting technological advances that really are moving ahead of the science and the research and the clinical applications. So I think this really opens up a new generation of how we can study the brain, in more naturalistic settings and in very young populations that we desperately need to be able to study and understand. Now, as I mentioned earlier on, AI is also having a huge impact in personalized medicine and radiology, and I'm sure you've all heard of it, it's the buzzword of the day. But the general idea is that, you don't explicitly program a computer to understand the data. You kind of feed it in, and you feed in as much as possible, and it kind of pulls out patterns in the data, and then you can input unknown data or naive data, and the machine will predict what that data is. So you can say, okay, here's a load of mTBI scans. Here's some new data. Tell us whether it's an mTBI or is it someone with a healthy brain. And, the machine will be able to learn the patterning of brain activity that underscores that. So it's a way of automating complex modeling, really, the be all and end all of it, and being able to develop precision outcomes and predictions. So, going back to some of the data that I talked about earlier on, here's brain connectivity, and this is one participant I selected at random, and you can see it does have a characteristic pattern to it, right? So the computer can learn that, and then we can put in new data and say, okay, is it someone that had a concussion or not? Now, integrating AI and Meg, has some great uses. And one of the problems with concussion research is, as I said earlier on, concussion symptoms are reported subjectively. You ask someone how they're feeling and they say, I've got a headache or I've got nausea. But it can mimic other conditions such as PTSD, depression, anxiety. And on any given day, some of us also report concussion-like symptoms, right? So here's some data from adults, who we looked at with concussion in blue and in pink, the controls, and we administered a concussion questionnaire saying, have you got a headache? And you can see that even in some of the controls, on any given day, they might say, oh, I'm tired, I didn't sleep well. And in concussion, some of them have reported no symptoms, they've got better in the time we scanned them. And when we look at the accuracy of machine learning models to detect which one is one or the other, it's not accurate 100% of the time. So this is actually quite difficult, right, to say you've had a concussion versus you've got some other illness or you're just having a bad day. So it shows relatively low specificity and sensitivity, but using the same AI, we can now put in someone's brain data and we can almost perfectly differentiate someone who's had a concussion versus someone who hasn't. Now, this is really exciting proof of concept, really, and it's got to be taken with a caveat that, this is low samples, but it's quite an exciting future, I think, for being able to detect it. So now that we've detected concussion in someone, everyone's different. Their brains are all different. Their symptoms are different. How do we treat them? Here's patient A, here's patient B. They've had a concussion, but their brain dysfunction can be quite starkly different. So with this, there are some new emerging therapies in concussion. Concussion is incredibly difficult to treat, but we've scanned your brain, we've got your individual profile. Now, how can we kind of treat that? And it naturally leads to that question, okay, you've diagnosed it, so what can you do? So one of the ways that we're trying in my lab is using neurostimulation. Now, there's many different ways. There's transcranial magnetic stimulation or transcranial electric stimulation, but it works by activating very subtly different areas of the brain. And we can promote repair and plasticity in the brain through this. And we've just had this kit installed at SickKids. And this really, offers us, again, a future of precision medicine for brain disorders where we can say, okay, we've scanned your brain, we're going to target this area, we're going to promote the plasticity and repair that your brain naturally has. And a lot of this work has actually been driven by Professor Adam Curtin out in Calgary. He looks at paediatric stroke. And, he's got some amazing pieces of kit where, he can integrate it with someone's brain image and then he can zap that bit of the brain and stimulate it and promote repair. And, we're saying now, okay, can we translate some of these findings and some of these techniques to more subtle brain injury like concussion and mTBI and the like? So there's this new exciting future, I think, of being able to bring these all together to try and, naturally promote and repair the brain. So we're coming to the very end. So I just want to say, thank you very much for listening. But we're moving towards a future, I think, of rapid, well-tolerated imaging, integrated with AI. It means we can accurately diagnose and help treat, brain disorders. And this is especially important in very young children who, we often can't ask about their symptoms or don't really comply very well. So this will be, I think, for concussion specifically, crucial in determining, return to play, return to work, return to school protocols, saying your brain has healed. You can go back, and if it hasn't, how can we treat that? So again, I know I've talked about a lot today, but we're really trying to embody this bench to bedside approach and having a transformative impact on the clinical and cognitive neurosciences that we do, to being able to have a tangible impact on child and more broadly adult health as well, especially with subtle or invisible brain injuries. So with that, thank you very much, all of you, for listening. I'd just like to thank all of my collaborators and institutions and funding partners. Thank you very much.
Thank you so much, Ben. We've got no additional questions. Here's my plug for anything last minute. Here's a comment. Thank you for a fabulous presentation. Very exciting work. Look forward to the future work, particularly with common comorbidities around depression or PTSD. And she's wondering, or he's wondering, if you might be able to comment on the use of QEEG in detecting structural or functional changes after concussion.
Yeah, so we've actually got a paper under review at the moment, and the revision is just about to go back in, where we put everyone in who's got mTBI and PTSD, and they have the same symptom profiles and overlapping anxiety and depression. Now, using these AI approaches, we can tease them all apart. The paper's not published yet, but it's very exciting, and we want to roll that out to anxiety and depression, comorbidities too. So it's moving quite rapidly there, actually. I'm quite excited for that paper to come out. And it's not at all tangential, but QEEG really can just be thought of as MEG. They really measure the same underlying brain processes. We use the same type of analysis techniques, and you can apply a lot of this machine learning to QEEG too, absolutely, to understand the functional changes. And, I think the OPMs that I briefly just described are actually, going to start to rival QEEG in terms of cost and ability to administer, far more so than the conventional MEG. But I kind of talked about MEG today, but they're really the same, measuring the same underlying brain processes. Yes, you can absolutely apply this to QEEG as well.
And one last question we'll take before we close. Can AI tell the difference between autism spectrum disorder and post-concussive injury resultant outcomes or impairment level?
I would be hesitant to say definitively yes, because the data is not there yet, but I would imagine yes. We are looking at, actually at the moment, neurodevelopmental disorders, including ASD, ADHD, OCD, MEG data, and applying these techniques to those and being able to stratify them all. Specifically ASD and post-concussion. We haven't done that yet, but we hope to in future, of course.
Well, thank you so much, Ben. That's the end of our time together today. I want to thank you for sharing your time and expertise for this fascinating discussion, and I think there's a lot more potential in the future.
Thank you very much.
Thank you all. Bye. Thank you for all our members and attendees for spending this time with us. We hope you depart with some practical knowledge to bring back to your organization. Join us on March 3rd at 11 a.m. Eastern when we bring you health system responses to the pandemic. MUHC reflections on lessons learned from the Montreal Children's Hospital. Join us on March 25th, 2021 for our virtual complex care pop-up entitled All In, Creating Synergy in Pediatric Complex Care. And for more information or to register, please visit childrenshealthcarecanada.ca. It's always great if you can watch live, as your questions and comments really enrich the discussion. But if you can't, the recordings of these sessions are made available after the fact on our Knowledge Exchange Network. So thanks again for joining us today. Thank you to Ben for this great presentation, and hopefully we'll see many of you back here on March 3rd. Bye, everyone.